Okay, in this question, we have a linear map which will simply reflect a vector in the line y equals x, which is the dotted line here. And we want to show that the vector 1, 1 is an eigenvector, find the eigenvalue, and the same thing for the vector 1, minus 1. So let's figure out where those vectors are. If this is 1 here, whoops, and 1 up here, then the vector 1, 1 lies on this axis of reflection, while the vector 1, minus 1 is 1 across, minus 1 down. It's pointing down here. 1 minus 1 is that vector. Now what's the reflection going to do to the vector 1 minus 1? Nothing. It's already on the axis of reflection. So we see that if you apply t to 1, 1, you just get the vector 1, 1 back. It's 1, 1 back again. And we want to write this as a constant times 1, 1. Obviously, the constant is 1. So the vector 1, 1 is an eigenvector with eigenvalue 1. It's an eigenvector of t, to be specific. With eigenvalue 1. And similarly, now what happens if we reflect the vector 1 minus 1 in this line y equals x? You can see instead of being down in this quadrant, it's going to flip over here. And we'll get the vector which is minus 1 in the x coordinate and 1 in the y coordinate. Okay? So this one is t of 1 minus 1. T of 1 minus 1, as we've seen from the geometric picture, it's minus 1, 1. And again, we want to write this as a scalar multiple of the vector we started with. Obviously, that scalar is minus 1. And this says that the vector 1 minus 1 is an eigenvector of t with eigenvalue minus 1. And that completes the question, well, part A of the question. While we're here, we may as well find the matrix that represents this map, and we're going to do that using the matrix representation theorem. The map T goes from R2 to R2, so the matrix A will be a 2 by 2 matrix. The first column equals T of the first standard basis vector 1, 0. So here is the first standard basis vector 1, 0. What happens to this vector under T? Well, when you reflect, it'll reflect up to sorry for the mess, the second standard basis vector, 0, 1. T of 1, 0 is 0, 1. So we note that T of 1, 0 equals 0, 1. And now, if you perform a reflection twice, you'll end up back where you were. So we can see that T of 0, 1 will take us back to 1, 0. So that was easy, we only had to really calculate one thing. And the matrix representation theorem says that these vectors are our two columns of A. So without any further calculation, we just write down A. The first column is T of 1, 0, which in this example is 0, 1. The second column is T of 0, 1, which here is 1, 0. And that's it.